Welcome to Circuit Analysis. I'm Jesse. We're going to look at the bolt circuit simulator again today, and I'm going to go over drawing a schematic. So before I get into it, I want to mention on circuitanalysis.com you can now do this bolt docs, and there's a bunch of notes here on how things work. So there's schematic drawing, part libraries, text editor, spice solver, and a waveform viewer section, so you can check out all of the details. So here we are in Bolt. We've got a new schematic, and this is the default component here, this Netlist component. And let's just do a open loop boost converter kind of thing, because that'll be a simple way to demonstrate this. There's an example file that's a similar idea. So we want to switch. You just drag these off. So you just click and hold down and drag. We're going to need an inductor, and we're going to need a diode. So we're going to use this Schottky diode here. Now these are in the right positions. This one we want to rotate, so you just select it and then you press the R key, and there's in this edit there's some things in here where you can rotate, but you're going to want to get used to the shortcuts. So then if we click off of here, you can move these little labels around. So you're going to click this one and then hold down Control so we can select both of them, and then just drag them up like that. And now we want this ground node as well, and we're going to do an input DC voltage source and an output load here, resistor. And then to control the duty cycle, we'll use this pulse. We want the pulse voltage source, so that's this one here. Now I want to connect everything together, so we'll hit the W key, and you can see that that switches to this crosshair, which means we're in wire mode. That's also this button up here, but it's easier to hit W for wire, and you can start drawing a wire just by clicking on the component and then click again here. That will end it. See, it gave it a random net name there of 8, and can start drawing another wire. You'll notice that it kind of starts, you can kind of move it around this way, and as you move it around it'll change the direction that it is drawing the corner of the wire. So we can just connect all these up, and then if you hit W again or escape, then it will get out of the wire mode. Now notice here we can drag this over. It made a little extra funky wire there, so we'll just click that and hit the delete key. That'll remove that. Notice that this is labeled as node 1, and this ground node here, if we connect it up, all it really does is just labels that net 0. So 0 is the default ground name for spice ground nodes. And we want to make this a little bit easier to read all of these, so we'll select all of this and drag it down. So we can move this one down here, and then this one up. Delete that. So now that we have the circuit set up, we're going to rename the parts and the nodes. So you can double click on these to change their name. I'm just going to call this VN for the input, and we'll just make it like 24 volts. And you can double click on these nodes as well. I'm going to name these in and out just to make them easy when we're looking at the waveforms. And I'm going to call this one D for the duty cycle. And we can call this one S just because it's the top of the switch here. So we'll make this load something smaller, like 10 ohms. And we can rename this. And that's pretty good for now. So if you'll remember from the overview first tutorial, the way that this builds the netlist, we can check out our netlist just by double clicking here. So this is the netlist so far. And if you remember the way that it builds the netlist, so you can grab these and resize them, but just loops through here and it adds together all of the templates. So to see the template, you can just double click on each of these and you can see, so here's the template for this one, and it's replacing these with the property names and the node names from the symbol. So if you click settings here, then you can see the property names, and these are the node or the pin names here. So now these are elementary parts. So you can see this is the full Netlist entry here, but the diodes and transistor, those have special models. So you'll notice if you double click on this, it doesn't have the model in the template here. Neither does this one. So where are the models for those? They're in this Netlist end. So it's got just a bunch of basic models for each part here. So that's what's being called out. This 5819, that one is here, 5819. And then you can see the 540, that one is here. So at this point we could delete all the models that we aren't using in here, or we can just leave them, it doesn't really matter. These are just default models for the rest of these parts. Down at the bottom here, there's the simulation options. So we're running a transient analysis right now. 1 millisecond and 5 microseconds is the maximum step size, so it won't take any larger steps. But SPICE is variable step, so it can do smaller than this depending on how quickly the signal is changing. So anyway, if we go back to the main Netlist, you'll notice this right here is all the parts, and then everything else is just coming from this Netlist end. So we can go ahead and run that and see what happens. So we got a first error here, and it's reminding us you got to save the schematic before you can run the simulation. So we'll go Control S, and I'll call it Boost Converter R1. Now we can run the simulation. So you couldn't see that because it was off the screen, but it popped up for a second, the actual ngSpice simulator. And I'll just point out here, you can do that right here, this selection, hide simulator or show simulator. That tells you if you want to see it actually pop up or not. So that's helpful for debugging sometimes. Now that the simulation's done, we can go over here and look at V out. And notice when you click here, it shows in the status the available waveforms. So it goes away after a few seconds, but you can click again if you want a reminder of what the options are that you can type in here. There's also some stuff up here. This is the part settings that was open before, but this here is the output log from the simulation. So you can look through that, see what kind of errors and stuff there are. These warnings are generally not that important, although it's saying that there's some unrecognized parameters that are being ignored in the model. It's using ngSpice 39, and it did complete the simulation. And then these here are some of the voltages when it was running the initial operating point analysis. So I guess one of the morals here is that these default models are pretty generic. It's not even using all the parameters that are listed in them, and so it's going to be best to figure out when you're actually selecting parts, go to the manufacturer's website and download the SPICE models for the specific parts. But this should get us started. So if we go back over here, what we notice right away is that it's starting off at 23 volts. So nothing's really happening. This output here is just whatever the input is. This thing may or may not be switching. You can see here we can add another plot on this plot with a semicolon and then do VD, and that puts it on a secondary axis over here on the right. The other thing we can do is make a new plot, and then we can just Control X. This one down to there. Now we have two separate plots, and if we click and drag, we can create a zoom section here. So we see this one is switching, and we haven't set any of these parameters up yet. But this S here, if we do another one, VS, So nothing's happening here, so that's the first thing. The output is just basically this voltage flowing through here and setting the output. So now there's two things we want to adjust here. One is we want to get this to actually be switching, and then the other is we want to add some filtering on this output and some initial conditions so that we can have it start off at 0 and see the output rise. So to scroll from left to right, I'm going to hold down Shift and use the scroll wheel on the mouse. And then to move up and down, you can just scroll. And then if you want to zoom in and out, it's the Control key, zoom in and out. So most of the shortcuts on here are pretty standard, things like Control C, Control V for cut and paste, and Control Z and Control Y for undo, redo. But you can go back to this list of docs here and scroll down, and there's a list of all the shortcuts right here. So yeah, a couple I didn't mention, we have the R for rotate, but you can flip horizontally and vertically. Got the cut, copy, paste. This one here, I guess, is one to point out. So might need to look into changing that at some point, but Control R is reload, so that reloads the whole program if you're having trouble with it, if it's crashing or something like that. But you got to be careful you don't do that when you mean to just do rotate, because then you'll lose your work. So make sure you do Control S often and save everything. Alright, so we're back here. Gonna move this over, get some more room, and put this capacitor down here. So this will be our output filter. I'm going to make that a little bit bigger, so maybe 100 micros. And we want this to have an initial condition. So in Spice, you do that with an IC statement. So we go double click on it here. We need to put an IC statement in here. And we could just say IC equals 0. That would be an initial condition. But a sort of fancier way to do it that I'm going to do here, you can right click, go into settings, and then we can make a new property here, and we're going to call it IC for initial condition, and we're going to set it to 0. Now if you do a regular left click on this display here, you can set it to both. So now you can see it's displaying IC equals 0. And now if we double click to go back into this template, we can do IC, and instead of setting it to 0, we can call in the IC property value. And we do that with the $ and the brackets, and then we're just going to put in here IC, and you can do capitals or lowercase, it doesn't matter because this is Spice is not case sensitive. And you'll notice whenever you're doing this stuff, well, this one here actually, it updates automatically. Some of these ones, they'll put a little bubble up here if it hasn't been saved. It'll run the latest update when you click play. You don't have to save it first. These properties, we can save that. Now we'll make sure that everything's saved and up to date, and we'll run this. So now you can see that's still not working very well. It's still starting off here at 23.4 volts, and this is one thing that I always forget. So if we double click on here, we can see it did work. We have the IC equals 0 on our capacitor here. But what we need to do is go into this Netlist end, go down to the transient analysis here, and there's this UIC statement that you have to add here for use initial conditions. And if you don't have that on the end, it will just ignore all the initial conditions. And we can move all those up a little bit. So now that we have that, you can see now it's starting off at 0 and it's rising up, but it's still not switching. So why is it not switching? Well, if we go into the Netlist, you can look at this IRF 540, and that's down here. And if you look at this VTO, this is the gate threshold voltage required to turn it on. You'll notice that's 3.16 volts, and this is going from 1 volt to 2 volts. So we want to change this to go from 0 volts to something above this. So a good driving voltage might be more like 12 volts for the FET. So let's do that. And now we have here a period of 2 microseconds and a pulse width of 1 microsecond. So it's basically switching at 1 over 2 microseconds, which would be 500 kilohertz, and it's got a 50% duty cycle. So let's see what that does. So now the question is, does this output make sense? Let's go over to Wikipedia here for the boost converter, and we can see the boost equation. The output is 1 over 1 minus D. So in this case we're saying we got a 50% duty cycle, so 1 over 0.5 would be 2. So we should be doubling the output voltage. We have 24 volts in, and we're getting, here you can see down here it says the output voltage is 43 volts. So it's not quite optimal. So one thing we can do is we can raise this up a little to make sure this thing can put out enough current for the load. So that boosts it up a tiny bit, and then we can play around with the value of this. Probably would be best to calculate what the actual power stage should be, but we don't have time for that. So you can make this bigger, can make it smaller. So there we go. If we make this smaller, it actually is able to boost it to a higher voltage. So now it's getting 50 volts, which is a little bit closer to that 48 volt ideal. Anyway, if we want to do an expression to easily see what this output voltage is, we can go back to the documentation here, and if you scroll down to the bottom, there's a summary of the different functions here, and we can see which one we might want to use. You can also right click here and do edit functions, and then you can see all the code for the functions in here. But if we just go back here, well, we could just get the last one. I mean, that might be the easiest way at this point. So we could either average over a range, or we could just do the Y last. Let's just do the Y last because that's easier. So we'll copy this, and we'll do Y last, and this here will be like V out. So there we go. So we got 50.15, and then we can Control S to save these settings here. So now, what if we want to get slightly fancy, because this has a lot of numbers in it, but what we are really interested in with this is the frequency and the duty cycle. So what we can do for that is, there's a few things we could do, but in here, so to make some variables dot param, we can give it a name, so we'll call this one F. Right now it's 500 kilohertz, so we'll just start with that. Make another one. We're going to call this one D for duty cycle. Make that 0.5. Now, if we want to change these values over here, and if we change the value of this to use the parameters in an equation, we use the brackets like this. So do 1 divided by F. Get a 1 in there. And then the pulse width would be D divided by F. I accidentally got an extra 1 in there. Okay, so now we're back to where we were. If we want to get rid of all this extra stuff, we can go to the settings and click on these. We can put none, and that will hide all of these values. Now we just have these two here. But now, say we want to make it even fancier. See, there's a lot of different ways to do the same thing. But let's say we wanted to make it so you could see the frequency and the duty cycle and adjust it on the schematic. So one way to do that, we might make 2 more properties on this, and we could call them F and D here, and we'll do 500 kilohertz and 0.5, and we're going to show both. And now we can just hide these other two here. And with these two, we've got to go back to the Netlist injector here. And we're going to move these parameters. So I did Control X out of there. And now we're going to go into the template for this guy. And we'll just put them in here. It's $, and these. So now we're calling the property value of this F and this D, which are set over here. So see, now we're back to where we started again. And if you click on here just to see the overall netlist, you'll see these are injected here with those values, 500 kilohertz and 0.5. So now we can just change this to 250 and run it again. And you can see how it's changed now. These are a little further apart. And we could change the duty cycle. So you can see now the output voltage is a little bit lower. It's not really going according to that formula, the 1 over 1 minus D. And that's probably because we aren't operating in continuous mode. That formula is only for continuous mode. So if we want to see what mode we're in, we can do another plot here. And we can look at the current through the inductor. So this is going to be an I of L1. And here it is. And if we want to see it a little better, we can uncheck some of these other ones. And here we are. So you can see we're definitely not in continuous mode here. The current in the inductor goes up and then it goes down and then 0 for a while. So we are in discontinuous conduction mode. So here's continuous, had that formula, discontinuous. So now we're operating more with this formula here, which allows the voltage to spike a lot higher at these peaks. So the last thing I wanted to mention is just a general sort of philosophy of how these are put together. So there's symbols, and there's wires, and there's nodes, and then there's labels. And the symbols are what create the lines in the netlist. The wires connect all the symbols together, and then the nodes are at each end of a wire and at every pin of a symbol. If you right click on these, you can see this JSON. This shows you what's kind of underneath in here, and you could update this and save it, and it would update here, but you have to be careful because you got to make sure that's formatted correctly. But you can see these connections here. These are the pins, so each one of those has a node. And if you go into this view, there's these here different options where you can change what you're looking at. So like if we want to see all the nodes, you can do all nodes. And now you can see every node on the corners and stuff. When you do sum, it just shows only nodes that have more than 2 connections. So like this one here, you like view sum. So that's kind of the default. It makes it look nice, like you're drawing a circuit. And also the net names. Net names are kind of attached to each wire. So if you do all of them, you'll see them on each wire. But if you do sum, then it'll just show it 1 per net. So it won't be on every single wire. And then we have hide same net names. This here is this on show by default, and that just means if you have 2 disconnected nets, it will show you. So like if I put another one of these here, see it shows that those are connected by putting this little line there, and if we uncheck that, that'll get rid of those. So if you give 2 nets the same name, like if I named this one here IN, then these 2 nodes would get connected, even though they're not connected by a wire. So then in here we have show pin numbers. So if you have some, it's only for subcircuits, but if I do all, you can see the pin numbers for each part, and that helps a little bit with troubleshooting sometimes. So if you go here and you do the settings, see these are the pin numbers here, and pin names, those also correspond in here with this JSON, these connections here, and settings in here, see these are the 3 pins. And we can also do pin names all. If you do that, that shows these names along with the numbers. Alright, that's it for today. Next time I'll go over more details on the subcircuits. For now, let me know if you got any questions, and I'll put some links in the description for downloading Bolt and joining the Discord, and we'll see you next time. Thanks for watching.